Welcome to the Deep Dive, where we don't just skim the surface of research, we plunge right into the heart of it, dissecting what truly matters and hopefully bringing you those aha moments that make you think differently. Today, we're not just looking at speed, we're talking about a kind of hyperspeed, really. A technological leap where every microsecond, and I mean literally every microsecond, can be the difference between mission success and, well, catastrophic failure. So maybe close your eyes for a second and imagine a scenario that just chills you to the bone. A huge earthquake has crumbled the city block, right, leaving this labyrinth of unstable rubble. Or maybe a chemical plant has suffered a catastrophic breach, unleashing an invisible toxic plume into the air. Scary stuff. Perhaps it's a military zone, shrouded in the chaos of battle, where critical intelligence needs to be gathered about some unseen threat. How do you find what you're looking for in these moments, whether it's a survivor trapped deep beneath concrete, the source of a hazardous leak, or maybe a hidden danger when sending human responders in is simply too risky, too slow, or, frankly, downright impossible? In these really harrowing situations, our reliance on technology becomes absolutely paramount. This is where unmanned ground vehicles, UGVs, and unmanned aerial vehicles, our drones, step in. They become our crucial eyes and ears, designed specifically to navigate these treacherous, unknown spaces. They're on the front lines, really, acting as extensions of our senses. But here's the monumental challenge they face. How do these autonomous agents reliably find and precisely locate targets in environments that are not only incredibly dangerous, but also notoriously noisy, unpredictable, and constantly changing? This is so far from a clean, sterile laboratory setting with perfect data. It's the grittiest, most complex reality imaginable.
And this is precisely the kind of problem where the power of particle filters, or PFs, truly comes into play. These are sophisticated algorithms, really quite remarkable, that are exceptionally reliable for modeling these complex real-world systems. Think about a drone weaving erratically through a collapsed structure, maybe, or the unpredictable diffusion of a chemical plume in gusty winds. These are highly nonlinear movements, very hard to predict. Or consider sensor noise that doesn't follow a neat, predictable bell curve pattern, which we call non-Gaussian noise. PFs are, in many ways, the ideal mathematical tool for these incredibly complex, uncertain scenarios because they can handle that inherent messiness of the real world. They don't need things to be perfectly linear or, perfectly Gaussian. However, for all their power and precision, particle filters have always had this glaring Achilles heel, their computational complexity. Historically, they've just been far too slow, often taking hundreds of milliseconds, sometimes even seconds, to run one cycle, which makes them pretty impractical for the real-time demands of critical time-sensitive applications where decisions need to be made in, well, a fraction of a second.
And that, my friends, is exactly what we're here to talk about today. In this deep dive, we're going to unpack some truly groundbreaking research. And I mean groundbreaking. Research that didn't just tweak particle filters around the edges, but fundamentally re-engineered them. They tackled that Achilles heel head-on, leading to an astonishing, almost unbelievable speed-up we're talking about, going from processing in milliseconds down to mere microseconds. This isn't just an incremental improvement, it's a radical transformation that opens up a whole new world of real-time autonomous localization. We'll journey through the brilliant algorithmic cleverness and the cutting-edge hardware wizardry that made this possible. And we'll explore why it's such a monumental game-changer for missions where every single second, every tiny fraction of a second, profoundly impacts the outcome. By the end of this deep dive, you'll get a genuine shortcut to understanding the very forefront of robotics and signal processing. You'll not only grasp the core concepts, but also discover some surprising facts about how seemingly impossible computational bottlenecks can actually be overcome, completely transforming what we thought was even achievable for autonomous systems. So, let's dive in. Okay, let's unpack this core problem a bit more. We started with the idea of dangerous unknown environments. And it's absolutely no exaggeration to say that precise autonomous localization in these settings is often a literal matter of life and death. Or at the very least, it determines the success or failure of a critical mission. We're really talking about the highest stakes imaginable here. Think about emergency response operations, like disaster relief in the immediate aftermath of a catastrophe, or crucial military applications where precise targeting or reconnaissance is paramount. These situations frequently require something highly specific: the localization of a contaminant, chemical, or biological source in an unknown environment, finding that needle in a very dangerous haystack. Let's maybe consider some concrete scenarios to really drive this home. Imagine a nuclear power plant incident, right? Or a train derailment releasing toxic chemicals. Sending human responders into a contaminated zone exposes them to unimaginable risks. Direct exposure to hazardous materials, unstable structures, maybe even unseen biological threats. Their mobility is limited, their endurance finite. It's just incredibly dangerous. Or picture a military operation where you need to precisely map a bomb site to understand its blast radius and locate unexploded ordnance. Or maybe search for a gas leak in a compromised facility without putting a soldier's life directly in harm's way. Our unmanned ground vehicles and unmanned aerial vehicles, our UGVs and UAVs, they offer not just an alternative, but a crucial, often indispensable solution. They can go where humans can't or really shouldn't, drastically reducing that human involvement and the associated risk. They can operate for extended periods, cover vast areas, and gather data in ways humans simply cannot.
That's the dream, isn't it? To send in a robot and have it do the dangerous work safely. But it's far from as simple as just, equipping a robot with a sensor and setting it loose. The fundamental, really gnarly challenge here is that these missions are conducted in conditions that vary drastically depending on the environmental factors that result in the sensor receiving noise-corrupted measurements. This isn't just a minor annoyance, it's the core obstacle. What it really means is that the data streaming back from the robot isn't clean or clear or unambiguous. Not at all. It's messy, it's ambiguous, often full of false positives, confusing signals, and constant interference from the environment itself. Imagine a sensor trying to detect a faint chemical signature while battling high winds, temperature fluctuations, and maybe reflections from surrounding debris. All of that environmental chaos translates directly into noise-corrupted measurements. This makes finding a target autonomously, with the precision required for a critical high-stakes mission, an extremely difficult, almost overwhelming task.
Yeah, so if you can imagine trying to find that tiny needle in a colossal haystack, but that haystack isn't just sitting still, it's actively moving, it's maybe on fire, there are strong winds whipping through it, and your eyes are blurry from smoke and dust. That's the kind of complex, noise-filled challenge these autonomous vehicles are truly up against when they're trying to locate something precisely. It's a sensory overload problem, really, where clarity is a rare luxury.
hmm And this brings us to the very heart of the technical problem these systems are trying to solve: state estimation. In simple terms, state estimation is about figuring out the current state, say, the position, velocity, or even identity of something that's moving or changing, based purely on noisy, incomplete observations. These estimation problems are typically represented by two mathematical models: a system model, which represents how the state evolves over time, like how a drone moves from point A to point B, and a measurement model, which represents the relationship between the actual state and the noisy measurements our sensors are picking up. In the past, engineers extensively relied on traditional filters, most notably the Kalman filter, to solve these state estimation problems. They're incredibly efficient and effective, I should say, especially for systems where the movements can be described by linear equations, and where the noise follows a very predictable bell curve-shaped pattern known as Gaussian noise. However, the reality in most of these critical real-time applications we've been discussing, disaster zones, battlefields, is far from ideal. The movements are typically nonlinear, meaning they don't follow straight lines or smooth, predictable curves. And the noise. It's almost always non-Gaussian, meaning it's erratic, bursty, and doesn't fit a tidy, predictable statistical distribution. This is precisely why traditional filters like Kalman filters prove to be less reliable in these real-world, highly dynamic, and unpredictable scenarios. They simply can't cope with the inherent complexity and unpredictability of nonlinear dynamics and real-world sensor noise, not without making significant, often inaccurate approximations anyway. In fact, numerous studies have consistently shown that particle filters, which we're about to really delve into, consistently outperform these conventional filters when faced with these challenging real-world conditions.
That's a really crucial distinction. So if we continue with our analogy, a Kalman filter is like having a perfectly tuned GPS for a road trip, where you're mostly on highways, moving in predictable ways. It's fantastic if you're tracking something moving in a relatively straight line, or maybe a smooth, gentle curve that can be easily approximated. But now imagine you're trying to track a tiny, agile drone dodging through a dense forest, or maybe a faint chemical plume swirling unpredictably around obstacles in a city. That's a wild, unpredictable curve. The Kalman filter trying to force that chaos into its neat, linear Gaussian box, it would quickly lose track. It would be constantly confused, unable to adapt to the true, messy reality.
Exactly, and that's precisely why particle filters have seen this growing popularity in signal processing and communication applications to solve various state estimation problems like tracking, localization, navigation, and fault diagnosis. Their inherent ability to precisely model and handle both nonlinearity and non-Gaussian noise gives them a distinct, almost unmatched advantage where traditional methods simply fall short. They don't try to simplify the world, they embrace its complexity, making them pretty much indispensable for accurately estimating states in these difficult real-time scenarios. Okay, so to truly appreciate the groundbreaking nature of this research, we first need to build a clear mental model of how particle filters, or PFs, actually work. At their core, PFs are inherently Bayesian in nature. This means they operate on probabilities, constantly refining their best guess about a system state as new information comes in. Bayesian statistics is key here. Their fundamental goal is intending to construct a posterior density of the state. In our context, that means estimating the most probable current location of a target or source based on the observed noisy measurements. Think of posterior density as the algorithm's updated, most confident belief about where something is after considering all the available and often very noisy data.
Okay, that phrase, posterior density of the state, still sounds quite academic, maybe a little intimidating. Let's break it down with a more intuitive metaphor. The posterior of the state is represented by a set of weighted random samples known as particles. Now, these particles aren't physical objects, right? They're little mathematical representations. Each particle is essentially a distinct guess or a hypothesis about the target's current state, its location, its velocity, whatever we're trying to estimate. And crucially, each of these guesses has a weight assigned to it, which signifies its probability or the filter's confidence in that particular guess. So you can imagine having thousands, maybe even tens of thousands, of tiny independent observers, each making their own educated guess about a target's location. The filter then intelligently combines their votes, but not just by counting them. It weighs them based on how well each guess aligns with the incoming sensor data. The more weight a particle has, the more confident the filter is in that particular guess, and the more influence it has on the overall estimate. Makes sense.
Precisely. Within this Bayesian framework, PFs operate in a continuous recursive loop, moving through two main conceptual stages: prediction and update. The prediction stage is where the filter tries to anticipate where the state will be next. It uses a system model, which describes the dynamics of what we're tracking, along with a complex mathematical tool called the Chapman-Kolmogorov equation, to estimate the probability distribution of the state at the next time step. It's essentially projecting all those particle guesses forward in time based on how it expects the target to move. Then comes the update stage. Here, new measurement data from the robot's sensors arrives. Fresh intel. The filter takes this fresh information and uses Bayes' rule, a fundamental principle of probability theory, to refine that prediction. It compares each particle's predicted state with the new measurement, adjusting their weights accordingly. Particles that align well with the new data get their weights boosted. Those that don't, well, they see their weights diminish. The key thing here is that PFs are an approximation-based method. They are employed when finding an exact analytical, mathematical solution to the Bayesian problem is intractable, meaning it's impossible or just computationally too expensive to solve directly, which is often the case in these complex, nonlinear, non-Gaussian real-world scenarios we keep talking about.
So it really is like having thousands of little observers, each with an initial opinion about where something is, and then the filter intelligently combines their votes to get the best overall picture. As new information comes in from the sensors, those votes are constantly being reevaluated and reweighted, tirelessly refining that picture to get closer and closer to the truth, even when swimming in a sea of noise. It's a pretty elegant, self-correcting system when you think about it. Now, let's zoom in on how these filters operate in practice, specifically focusing on a common and foundational type known as the SI filter. That stands for sampling, importance, resampling. And it's basically a three-step dance that happens recursively over and over again for every new piece of sensor data that comes in. First, you have the sampling step. This is where particles from the prior distribution are drawn. What this really means is that based on what the filter thought the target was doing in the previous moment, it uses its system model to propagate those existing particles forward in time. It's like each of our thousands of observers takes their current best guess, and then, considering how the target might move, projects that guess into the near future, creating a whole new set of potential locations. This step essentially generates new hypotheses about the target's current state. Where could it be now? Next comes the importance step. This is used to update the weights of particles based on input measurements. Here's where the rubber really meets the road, so to speak. New sensor data comes pouring in. The filter takes this raw data, looks at each particle's projected guess. It then compares that guess to what the new sensor data is actually reporting. If a particle's guess aligns well with the new data, meaning if the sensor measurement would be highly likely if that particle's guess were true, then its weight, its confidence score, increases. Conversely, if a particle's guess doesn't match the new data well, its weight decreases, sometimes significantly. This step is where the filter actively learns from the real-world measurements. It's crucial. Finally, we hit the resampling step. This is absolutely critical because without it, the filter runs into a serious problem called weight degeneracy. Over time, in a complex system, what happens is a few particles might accumulate extremely high weights, while the vast majority end up with very, very low weights, becoming effectively useless or degenerate. They contribute almost nothing. Resampling addresses this by essentially discarding particles with lower weights and replicating particles having higher weights. It's like weeding out the statistically improbable guesses and then making more copies of the most promising high-confidence guesses. This ensures that the filter always focuses its precious computational power on the most likely areas of the state space, preventing its collective intelligence from becoming too spread out and ineffective. It keeps the particle set healthy and focused.
And this resampling step, despite its critical importance for maintaining filter health, is precisely the crucial bottleneck that has plagued particle filters for decades. It's the big one. Remember, PFs apply a recursive Bayesian calculation, which means that in each iteration, all particles must be processed for sampling, importance, and resampling steps. The fundamental inherent problem is that the resampling step in its traditional form is inherently sequential and cannot be parallelized. You just can't easily break it up. Think about it. To decide which particles to discard and which to replicate, you first need to know the weights of all particles relative to each other. You need that global picture. You typically need to calculate their cumulative distribution function and then draw random numbers against that function. This means you can't simply have different parts of the computer working independently on different sets of particles for resampling, because each decision depends intrinsically on the global distribution of weights across all particles. It's a global dependency that forces a sequential operation, one step after another.
Yeah, you've really hit on the core challenge there, that sequential nature is the killer. To use an analogy, imagine you're trying to sort a massive deck of cards, say thousands of cards, and then redistribute them based on their value. But to do that properly, you first need to see every single card and its value before you can make any moves, right? You need the full picture first. Then you have to redistribute them all based on those values, perhaps throwing out the lowest value cards and making copies of the highest value ones. Now, if you try to have multiple people sort different piles simultaneously without each person knowing what the others were doing or the global distribution of all card values, it would quickly go wrong. You'd end up with a jumbled mess, not a properly sorted and redistributed deck. It's kind of why resampling has historically been such a stubborn sequential process. It relies on a global understanding of all the particles' weights before it can operate effectively.
Exactly. And the consequence of this inherent sequential nature is enormous computational complexity, and crucially, the execution time is directly proportional to the number of particles. This is a killer for real-time systems. If you need thousands or maybe tens of thousands of particles to achieve the necessary accuracy for, say, tracking a fast-moving object or precisely locating a tiny chemical leak, and often you do need that many for robust performance, then each resampling step, because it has to wait for everything else to finish processing all particles, slows the entire process down to a crawl. It becomes the limiting factor. This severely inhibits the use of PFs in various real-time applications wherein a large number of particles need to be processed to obtain a good performance. Missions that demand instant sub-millisecond responses become simply impractical, consigning particle filters to offline analysis or less time-critical tasks. It's been a classic computational bottleneck that has frustrated engineers for years.
Yeah, a real roadblock. Okay, here's where it gets really interesting, and frankly, a bit jaw-dropping for anyone who's wrestled with this problem. This research isn't just about tweaking existing code or making minor optimizations. It's about rethinking what was considered fundamentally impossible, or at least incredibly difficult. Parallelizing that notoriously sequential resampling step. The researchers propose a modification to the existing particle filter algorithm, which enables parallel resampling and dramatically reduces the effect of the resampling bottleneck. This isn't just an improvement. It's a profound shift in how particle filters can operate, fundamentally altering their speed profile. It's a big deal.
Absolutely. The core algorithmic innovation, which they detail in their proposed algorithm 2, is genuinely ingenious. Instead of one massive filter trying to process all n particles sequentially, the core idea is to use a network of smaller filters termed subfilters, each processing independently and concurrently. Think of it as breaking down that single colossal sorting task into many smaller, much more manageable sorting tasks that can happen at the same time. The processing of the total N particles is partitioned into K subfilters so that at most NK particles are processed within each subfilter. This architectural change alone immediately reduces the overall computation time by a factor of K. Imagine dividing a massive job among K workers who can all operate simultaneously. That's an immediate significant speed advantage right there, K times faster, roughly. But the true secret sauce here, the really brilliant stroke that unlocks the parallel resampling, is the novel additional particle routing step they introduced. This step distributes the particles among the subfilters and makes the parallel implementation of resampling possible. What's truly fascinating and quite clever is that this routing isn't an extra time-consuming overhead. It's cleverly integrated with the sampling step within the existing architecture, meaning it does not require any additional time for computation. It's not an added delay, it's woven into the seamless flow. This routing ensures that particles, even though they're being processed in independent subfilters, can still effectively interact and share information, which is absolutely critical for maintaining the overall filter's accuracy and integrity. They aren't totally isolated.
Right. So it's not just a brute force approach of throwing more computing power at the problem and hoping for the best. It's an incredibly elegant solution. It maintains the statistical integrity of the overall filter by ensuring that particles can still interact and influence each other even when they're processed in parallel within these smaller distributed subfilters. This is critical because if they were completely isolated, you wouldn't get that collective intelligence, that sophisticated Bayesian estimation that makes particle filters so powerful in the first place. They found a clever way to share the computational load without losing the big picture or compromising the filter's core function. It's like orchestrating a highly complex dance where everyone moves independently but somehow in perfect synchronicity. And here's where the jaw-dropping reality sets in. This isn't just about making particle filters faster. It's about making them fast without any compromise on accuracy. This is huge. The researchers meticulously compared the estimation accuracy of the standard algorithm with the modified algorithm across various scenarios, and their conclusion is definitive. They infer that the modified and the standard approaches do not vary significantly in terms of estimation error. Think about that for a moment. You're getting orders of magnitude improvement in speed while retaining the precise, reliable estimations that make these filters so critical for high-stakes applications. This truly is the holy grail for engineers and scientists working in real-time systems. You get the best of both worlds. Unprecedented speed coupled with unwavering reliability. That's the dream, isn't it?
The performance leap is truly staggering, almost unbelievable when you first see the numbers. For processing 124 particles, which is a common and often necessary number for robust performance in many applications, the modified algorithm achieves an astonishingly low execution time of about 5.62 seconds when implemented on an FPGA. Microseconds. Now let's put that into perspective. A conventional software-based CPU implementation running on a high-end Intel Core i7-7700 with 8 cores clocking at 3.60 gigahertz, a pretty powerful modern processor took approximately 64 meters for the same task. 64 milliseconds. We're talking about an improvement from milliseconds down to microseconds. That's more than a 10,000-fold speedup. It's hard to even wrap your head around that. This isn't just faster, it's a paradigm shift in responsiveness. Moving from delays that are noticeable to humans or problematic for rapid robotic control to essentially near instantaneous processing. This kind of speed completely transforms what's possible for real-time autonomous systems.
Wow. Okay, that speedup is incredible, but it didn't just happen in a vacuum, right? This modified SR algorithm isn't just some theoretical breakthrough on paper. It's brought to life on a high-speed and dedicated hardware architecture, incorporating pipelining and parallelization design strategies using an Arctic 7 field programmable gate array, or FPGA. The choice of hardware here is as critical and innovative as the algorithmic modification itself, acting as the powerful engine that drives this newfound speed. You need both parts. To really grasp why an FPGA is so crucial here, let's use an analogy. Think of a traditional CPU, like the one in your laptop or smartphone, as a really powerful general-purpose toolbox. It's incredibly versatile, capable of doing many different things pretty well, running spreadsheets, browsing the internet, playing complex video games. But it's fundamentally sequential at its core, designed to execute one instruction after another, even if it does it very, very quickly. An FPGA, on the other hand, is more like a custom-built, hyper-specialized machine tool. Instead of being programmed with software instructions running on fixed hardware, it's literally rewired at the hardware level. You configure it to perform one specific, complex task with unparalleled efficiency, perfectly optimized for that task right down to its internal logic gates. You're essentially building the circuit for the algorithm, rather than just running software in a fixed circuit. Big difference.
That analogy perfectly captures it. FPGAs are unique because they offer this unparalleled flexibility to design custom, massively parallel architectures right down to the gate level. Unlike CPUs or even GPUs, which have fixed general-purpose architectures, an FPGA allows you to configure its internal logic blocks and interconnections to precisely match the computational needs of your specific algorithm. You can create hundreds or even thousands of custom processing units working in parallel, tailored specifically for the particle filter's operations, the sampling, the importance weighting, the resampling. This makes them absolutely ideal for accelerating computationally intensive, highly parallelizable algorithms like this modified particle filter, where you need to process many particles simultaneously and manage very specific, high-throughput data flows. Flows that a general-purpose CPU simply can't achieve with the same energy efficiency or raw speed. It's really about building the perfect hardware engine for your specific software task. The top-level architecture of the specific design is particularly brilliant in its simplicity and effectiveness. It utilizes a filter bank consisting of K subfilters working in parallel, just as we discussed with algorithm modification. So you can imagine K identical independent processing units laid out on the chip. Binary measurements, which in their source localization example came from photodiodes, along with the UGV's current position data, are fed into this bank. Crucially, the system also incorporates its own dedicated high-speed random number generators. These are absolutely essential for both the initial sampling of particles and the resampling process within the particle filter, ensuring true randomness and avoiding performance bottlenecks that could come from relying on external or slower random number sources. Each subfilter then operates on its assigned subset of particles, performing the sampling, importance, and that crucial local resampling steps concurrently, all happening at once.
And the key design features they built in truly highlight the meticulous engineering that went into making this approach so effective and also practical. Let's start with modularity and scalability. The design is described as adaptable and straightforward, as it allows us to customize the number of subfilters. This isn't just a nice-to-have feature. It's really foundational to the whole approach. It means you can easily scale it up or down to process a large number of particles without increasing the execution time by using additional subfilters. For an engineer designing a system, this is invaluable. If your application initially needs, say, 124 particles for decent accuracy, you might use 64 subfilters. But if you later realize you need 4096 particles for even greater precision in a tougher environment, you can potentially scale the design to, say, 256 subfilters on a larger FPGA. The execution time per iteration remains roughly the same because you've simply added more parallel workers to handle the increased load. It's like adding more lanes to the highway. The traffic still flows smoothly even with more cars.
Right. And another incredibly clever trick is implemented to achieve memory efficiency. This is quite neat. A straightforward implementation of this parallel algorithm, especially with K subfilters, would typically require two 8K memory elements, basically, double the memory. One set for storing the currently sampled particles and another completely separate set for storing the resampled particles ready for the next iteration. But they dramatically reduce this memory footprint down to just K memory elements, each of depth M, using a dual-port RAM. So they halved the memory requirement. The innovation here lies in how they manage the resampling without needing that completely separate memory bank for the outputs. Instead of storing the replicated or discarded particles themselves during resampling, they efficiently store only the indices of these particles, pointers essentially. When a particle is replicated, they use a temporary register to hold the original particle's data while the new copy is written to the correct index location, preventing data overwriting issues. This intelligent use of memory not only reduces the overall hardware resources needed on the FPGA, which saves cost and space, but also makes the memory access more energy efficient, a critical consideration for battery-powered autonomous vehicles out in the field.
That is clever. Okay, and then to manage the potential communication complexity that could arise with a large number of subfilters, all needing to potentially share info, they employ a simple ring topology to exchange particles between subfilters. This is a beautifully elegant solution, really. Instead of every subfilter needing to be able to talk directly to every other subfilter, which would create this massive bandwidth-hungry spiderweb of connections on the chip. Communication is limited primarily to immediate neighbors in a ring structure. This keeps the communication overhead low and predictable, even as you scale up the number of subfilters. It's like a bucket brigade where information is passed efficiently from one person to the next in line, rather than everyone trying to shout across the entire line at once. This simplicity is vital for maintaining high-speed operation and predictable latency. No traffic jams.
hmm And all of these meticulously designed features combine to deliver truly impressive real-time capabilities. We've already highlighted the extremely low execution time of 5.62 seconds. This translates directly to a phenomenal sampling rate of 178 kilohertz. To put that in context again, it means the system can process new sensor data and update its state estimate 178,000 times every single second. That's blisteringly fast. This incredible speed is possible precisely because all the subfilters are operating in parallel, constantly processing their portion of the particles, with the particle routing and communication handled efficiently by that ring topology. This level of responsiveness is what transforms particle filters from a powerful but historically slow tool into a truly real-time, mission-critical component for dynamic systems.
And one of the perhaps understated beauties of this architecture is its inherent flexibility. It's not a one-trick pony hard-coded just for, say, light source localization. As the researchers explicitly note, the proposed architecture is not limited to a single application, and the design can be easily modified for a wide variety of other particle filter uses. The sampling and resampling blocks are highly generic. The primary component that needs tweaking for different applications is usually the importance block. This is the part that calculates particle weights based on specific sensor data and the measurement model for that particular problem. So, whether you're trying to track a drone, localize a radio signal, or maybe even predict the path of a biological agent, the core parallel framework remains adaptable. You just need to swap out or modify the sensor interface and weight calculation logic. This makes it a potentially foundational building block for many future autonomous systems, not just a one-off solution.
That's right. And if we were to take a quick peek inside one of these subfilters, you would see those core submodules. Sampling, importance, and resampling all working together. Notably, the sampling and importance stages are cleverly pipelined. This means they operate like a miniature assembly line within each subfilter. As soon as one particle finishes its sampling calculations, the next one can start sampling, even while the first one moves on to the importance calculation stage. This overlapping execution further enhances efficiency and significantly reduces the overall processing time for each individual particle within the subfilter, maximizing the throughput. It squeezes out even more performance. Now, when we look at the numbers for resource utilization on the Arctic 7 FPGA, they detailed this in their set 10. Table 2, it reveals the practical trade-offs involved in high-performance hardware design. It's not magic, there are limits. As you'd expect, resource utilization increases proportionally with the number of subfilters. More parallel units means more hardware. For instance, they report that for a design using 64 subfilters, 64% of the slice LUTs, lookup tables, which are the basic programmable logic units on an FPGA, are used. That's a fair chunk of the chip. Based on this scaling, they estimate that a maximum of approximately 90 subfilters can fit onto a single Arctic 7.FPGA platform of the type they used. This clearly illustrates that while parallelization brings incredible speed, it comes at a direct cost of physical hardware resources. An engineer planning a system needs to weigh these factors carefully, considering the required performance versus the available FPGA size and, of course, cost. They even provide a simple, elegant formula for the execution time, which is TSIR, 4 equals 4nk plus TCLK. This beautifully illustrates the direct relationship between the number of subfilters and performance. Here, n is the total number of particles, k is the number of subfilters, represents a small constant overhead like communication time, and TCL is the clock period of the FPGA. This formula clearly shows how increasing k, the number of parallel subfilters, directly decreases the 4nk term, which dominates the execution time for processing n particles. More parallel workers means the entire job gets done faster. It quantifies the speed up.
This then brings us right to a classic engineer's dilemma, doesn't it? There's a clear and unavoidable trade-off between the speed and the hardware utilized. You can't have everything for free. For instance, the researchers found that using a single subfilter uses a mere 1.4K, 1% LUTs to process 256 particles, and the time taken for SIR operations is around 1,075 clock cycles. Coming out. That's incredibly efficient on resources, perfect for maybe a low-cost, low-power application where speed isn't the absolute top priority. On the other hand, an 8-subfilter design takes only 178 clock cycles for SIR operations, but utilizes 11K, 8% LUTs. Okay. So you gain a massive speed boost, almost a 6-fold reduction in clock cycles in that example, but comes at a cost of significantly more physical resources, more logic gates being used on the FPGA. This isn't a flaw. It's just a fundamental reality of hardware design. The key for engineers is always finding that sweet spot the right balance for your specific application's requirements, available budget, and power constraints. ensuring you get the performance you absolutely need without over-engineering it and wasting precious resources. It really highlights the practical reality of high-performance computing out in the field. You gain incredible speed and real-time responsiveness, but it often comes at a cost of physical hardware resources, like the number of LUTs on an FPGA, or maybe increased power consumption. The true genius, I suppose, lies in an engineer's ability to navigate this trade-off effectively, finding the right balance to optimize for their specific mission, whether that prioritizes ultra-low power, maximum possible speed, or some careful balance of both. Okay, so this isn't just about theoretical speedups on a chip or elegant algorithms on paper. The researchers took this breakthrough and immediately demonstrated its concrete, real-world impact with a practical proof of concept, which is great to see. They developed a novel source localization model, creating a sort of mini ecosystem to test their accelerated particle filter in action. The setup involved an omnidirectional light source, basically just a point of light emitting in all directions, which served as the target, the source that needed to be localized. Simple but effective. Mounted on top of the UGV, their unmanned ground vehicle was a photodiode housing. This housing contained an array of photodiodes, acting as a sensor to measure the relative intensity of light coming from different directions around the UGV. And to make it even more practical and representative of trying to figure out direction in a complex environment, the space around the UGV was conceptually divided into 8 sectors with 45-year angular separation, meaning each photodiode was effectively monitoring a specific wedge-shaped slice of the environment, giving the UGV directional awareness.
Exactly. The scenario they meticulously modeled was a classic search and detect mission. You have a stationary source, the light, and a moving sensor mounted on the UGV. The UGV's mission was programmed to actively traverse in the direction of the source and eventually converge at the source location, using the sensor measurements processed by the particle filter to guide its path. This nicely simulates the critical task of an autonomous robot searching for, say, a radiation hotspot or a chemical leak, where it needs to move towards the highest concentration or intensity of the target signature. The particle filter, running super fast on the FPGA, was constantly processing the photodiode readings, updating its estimate of the light source's location, and in turn, feeding commands back to direct the UGV's movement, closing the loop in real time.
And even with a seemingly straightforward omnidirectional light source, real environments are never simple, are they? The researchers wisely consider that reflective objects and other stray light sources are potential sources of noise picked up by the sensor, producing false detections. End quote. So it's not like it's operating in a perfectly dark room with only the target light. You might have the target light source, but also reflections bouncing off walls, or maybe other ambient light sources confusing the sensor readings. This makes the localization problem much more challenging, much more realistic, and truly tests the robustness of the particle filter. Can it handle that messiness?
And this is precisely where the inherent power and resilience of particle filters really shines through, especially this accelerated version. To realistically model this pervasive real-world noise, they introduced 2 key parameters into their simulations and model. I, which represents sensor imperfections and calibration errors, sensors are never perfect, and I, which models the probability of background noise activity or clutter, those false detections. What's absolutely critical here and really demonstrates the algorithm's strength is that even when they tested the system with a high noise probability backer, setting it as high as 0.6 in some experiments, which means there was a 60% chance that any given sensor measurement was just random clutter noise rather than a true signal from the source. That's a lot of noise. Even then, the PF algorithm proved robust enough to localize the source. It wasn't fooled by the overwhelming amount of false information. It managed to cut through the noise and find the real signal.
Wow, 60% noise is intense. And they provided a really powerful visual in their Figure 11, which graphically illustrated this 2D source localization result. You can see the UGV starting at coordinates 38, TAF4, quite a distance from the target light source. Yet despite all that noise and the initial uncertainty, the UGV successfully localized the source, which was situated over at 6022 with an impressive final estimation error of 0.5. An error of just half a unit in a 2D space, even with that very high noise probability of V equal 0.6, is incredibly precise. That's amazing. It unequivocally demonstrates that this system works under challenging, noisy, and ambiguous conditions, the very situations where traditional, less robust filters would likely fall apart or give wildly inaccurate results. This is a real testament to the combined power of the modified algorithm and the speed of the FPGA hardware implementation.
Mhm. And building on that, their Figure 12 provides another crucial practical insight. With an increase in noise probability, the number of time steps or iterations required to localize the source also increases. This makes intuitive sense, right? The more hazy or noisy the world is, the more measurements the filter needs to take, and the longer it takes to achieve a confident, precise estimate that meets the accuracy threshold. For example, they show that at a bet of zero point 0.1, so 10% noise, localization might take around 20 time steps, but at bet of zero point 0.6, that heavy 60% noise, it could take maybe 40 or 50 time steps to converge. The source is considered localized when the estimation error is less than the predetermined threshold, which is 2.5 in our case, for that specific plot. This isn't really a limitation, it's an expected and manageable characteristic that actually speaks volumes about the algorithm's resilience. It shows that the filter maintains its accuracy, it doesn't fail, even if it has to work a bit harder and take more time when faced with extreme levels of environmental interference or noise. It just needs more data points to be sure.
Right. And this clearly illustrates the algorithm's profound resilience, its toughness. It might indeed take more time steps, it might take more iterations when things get really noisy, but the critical takeaway is that it will reliably find the target. It converges even in incredibly challenging, extremely noisy conditions. This isn't just an academic detail, it's about building autonomous systems that are truly dependable when the stakes are highest, when human lives might be on the line or a critical mission depends on it, and when the conditions are guaranteed to be at their absolute worst. You need a system that doesn't just work perfectly in a clean lab, but works reliably when everything is going wrong. This research seems to deliver that real-world robustness, which is fantastic.
And the researchers didn't stop at just 2D localization on the ground. They successfully extended to 3D in a MATLAB software model, which is a critical and necessary step for many real-world applications, especially those involving aerial vehicles or complex indoor environments. This involves simulating an unmanned aerial vehicle, UAV, with 16 sensors designed to effectively scan the entire 3D space. So instead of just moving on a flat plane, the UAV could now navigate through depth, height, and width, searching in 3 dimensions. They provide a specific example. A source located at 40 hosted 5,025 in 3D space, with the UAV initially starting way over at 10,000 zerodome. The simulation showed the UAV successfully localizing the source with an estimation error of 0.83, demonstrating the feasibility in 3D.
Wow, okay, extending it to 3D immediately brings to mind incredibly impactful real-world applications, doesn't it? You can imagine autonomous drones precisely mapping the invisible boundaries of a chemical plume spreading through a complex industrial facility in 3 dimensions, or accurately identifying radiation hotspots in a contaminated zone from a safe standoff distance, pinpointing the source not just on a map, but in vertical space too. Think of drones tirelessly searching for survivors in the multi-layered chaos of an urban disaster zone, like a collapsed building, where the environment is inherently 3-dimensional and profoundly unpredictable, with structures both above and below ground level. The fact that this particle filter framework is robust, incredibly rapid thanks to the FPGA, and demonstrably scalable to 3D means the implications for hazardous missions are just enormous, significantly reducing human risk, dramatically improving response times, and providing unprecedented situational awareness in complex spaces. This technology is truly about pushing the boundaries of what autonomous perception can achieve in the toughest spots.
To truly appreciate the significance and the unique strengths of this particular piece of work, it's essential to place it in context. We need to compare it directly with existing state-of-the-art implementations. Their Table 3 provides a very clear head-to-head comparison against previous FPGA-based designs for particle filters, as well as against software-based approaches that leverage powerful GPUs or specialized digital signal processors, DSPs. This comparison precisely illuminates why their design doesn't just improve upon, but fundamentally stands out from what came before it in the field. Okay, let's talk about speed first, which is arguably the most dramatic differentiator here. Their design achieves that phenomenal sampling rate of about 178 kilohertz for processing N equals 2024 particles, 178,000 updates per second. Now let's contrast that with other notable FPGA implementations mentioned in the literature. Athali et al., for example, achieved approximately 16 kilohertz, albeit for 2048 particles. Agrawal et al. Reached 42 kilohertz. Yi and Zhang managed 46 kilohertz for 1,024 particles, and Seleshi et al. Hit 18 kilohertz. This new design isn't just marginally faster, it's often a factor of 4 to 11 times faster than previous state-of-the-art FPGA-based solutions for similar particle counts. That's a huge leap. This means it can update its estimate far more frequently, leading to much more responsive control for fast-moving robots and more accurate tracking of dynamic targets. Furthermore, while software-based GPU implementations can certainly be fast, they often come with significant drawbacks concerning hardware feasibility for embedded autonomous systems, things like higher power consumption, greater physical size, and less flexibility for custom, low-level optimization compared to what you can achieve with an FPGA. Another absolutely critical differentiator is scalability. The paper highlights that the resampling in our architecture is local to the subfilter, and the ring topology employed limits the communication to adjacent subfilters, thereby reducing the routing overhead. This is a profound architectural advantage. In many other parallel particle filter designs, especially when you try to distribute the resampling globally across many processing units, you encounter immense challenges with high communication overhead between multiple processing elements. It gets choked. As you add more processing units to handle more particles, the amount of data that needs to be constantly exchanged between them can quickly become a massive bottleneck, potentially negating any speed gains you got from parallelization in the first place. By making resampling local to each subfilter and using that simple, efficient ring topology for only essential particle exchange between neighbors, this design elegantly sidesteps that communication explosion. It allows for genuinely efficient scaling to a large number of particles and subfilters without getting bogged down or choking on its own data traffic. That's key for future growth.
Right, that local resampling and ring communication seem like really smart design choices. And finally, there's the significant advantage of modularity and flexibility in implementation that you touched on. Many high-performance designs these days often rely on high-level abstraction tools like HLS, high-level synthesis, which can simplify initial development but often limit the fine-grained optimization you can achieve. It's like a black box sometimes. This design, however, is completely hand-coded in Verilog. For those unfamiliar, Verilog is a hardware description language, like VHDL, that gives engineers granular control right down to the very logic gates and flip-flops of the FPGA. This level of control means they can meticulously tweak the design parameters to an unparalleled degree, optimizing for specific performance goals or resource constraints for a given application. This ensures that the design can be easily integrated into a multitude of PF applications, because its fundamental building blocks are highly adaptable and reusable at a low level. This granular control is a huge advantage over more rigid, potentially less optimized implementations generated from higher-level tools. So the bottom line here seems incredibly clear. This research isn't just incrementally better. It provides a fundamentally more efficient, more robust, and critically more scalable solution to a long-standing critical challenge in particle filter implementation. By intelligently redesigning the algorithm to break the sequential bottleneck, and then leveraging the inherent parallel processing power of FPGAs through careful hardware design, it truly makes real-time particle filters a practical and deployable reality, especially for complex, high-stakes autonomous applications where they were once simply too slow to be considered feasible. It really feels like a game changer.
It really does. And this leads us directly to the crucial so what question. The immediate implication is that the low execution time, i.e. high input sampling rate, makes our architecture ideal for real-time applications. This isn't just about making existing things run faster, it's about enabling entirely new capabilities for autonomous systems that simply weren't possible before because the perception loop was too slow. Now, robots can react and adapt to their environment with unprecedented speed and precision.
Absolutely. And this breakthrough isn't limited to just hazardous source localization, as compelling as that application definitely is. The proposed PF framework and its hardware realization would be incredibly useful for the signal processing community for solving various state estimation problems, such as tracking, navigation, and positioning in real time across a truly vast array of fields. Think about the broader implications here. Autonomous vehicles, like self-driving cars, navigating incredibly complex urban environments, dense with pedestrians, cyclists, other cars, where split-second decisions based on noisy, rapidly changing sensor data from LiDAR, radar, cameras are absolutely paramount for safety. This kind of speed could be revolutionary there. Or consider high-precision medical imaging, maybe during surgery, that needs to adapt in real time to subtle patient movement during delicate procedures to maintain accuracy. Even advanced human-robot interaction, where understanding nuanced human intent, gestures, and movement needs instant, robust processing for seamless and safe collaboration. This technology, this combination of algorithmic insight and hardware acceleration, has the potential to revolutionize countless fields where robust, real-time perception and immediate decision-making are not just desirable, but absolutely essential. It opens so many doors. Hashtag outro. So we've taken quite a deep dive today into the fascinating world of particle filters, a journey that began with understanding their powerful Bayesian foundation, allowing them to make remarkable sense of incredibly complex, noisy data, and then confronted that stubborn computational wall they've always hit with that inherently sequential resampling step. It was a classic engineering dilemma, a real performance bottleneck.
And we saw how a truly clever algorithmic modification Introducing that network of parallel subfilters, combined with an ingenious, essentially zero overhead particle routing step, managed to break through that wall. It enabled the parallelization of that seemingly impossible resampling process, fundamentally transforming the filter's execution speed without sacrificing any of the crucial accuracy that makes particle filters so valuable in the first place. Best of both worlds, really.
Right, and then how dedicated FPGA hardware, those custom-built hyper-specialized processing engines, brought this theoretical breakthrough to vibrant practical life, delivering unprecedented speed and efficiency. We're talking microseconds now, not milliseconds, making it truly practical for real-world, high-stakes missions where traditional CPU-based systems, for all their general-purpose power, just couldn't keep up with the demands of instant perception and decision-making.
The profound impact of this research is clear. It means autonomous systems can now potentially precisely locate critical sources or track targets in noisy, unpredictable environments with much greater speed and reliability. From mapping hazardous chemical spills or radiation leaks to conducting intricate military reconnaissance or complex search and rescue operations in disaster zones, it significantly reduces human risk by allowing robots to go into harm's way and dramatically improves response times, paving the way for safer, faster, and far more effective remote operations across many industries.
This work truly demonstrates that even deeply embodied, seemingly fundamental sequential computational bottlenecks, those problems we might have thought couldn't possibly be broken down or significantly sped up, can often be overcome. Overcome with a fresh, inventive perspective on both the algorithms themselves and the specialized hardware designed to execute them efficiently. It really leaves you wondering, doesn't it? What other impossible to parallelize problems, lurking in the shadows of real-time computation across science and engineering, might benefit from a similar radical rethinking? And what new transformative autonomous capabilities could that unleash in our world, making the seemingly impossible, suddenly perhaps, a reality?